Okay, hello everyone. I'm Chen from Nanjing University. Today I'm going to talk about evaluating the effectiveness of deep learning models for foundational program analysis tasks. And this is the outline for the talk. Riding on the starting advancement of deep learning, deep neural networks have demonstrated remarkable capabilities in semantic program properties. For example, bug detection, program repair, code documentation generation, and so on. However, a key question remains under-addressed. That is, how far can we push deep learning models in the field of program analysis? Are they even capable of solving tasks that are traditionally in the realm of foundational static analysis? The response to this question has a profound impact on the programming language community. If the answer is yes, neural networks can become a viable alternative for developing static analysis applications with their own advantages, for example, easier to create with higher efficiency, etc. On the other hand, if the answer is no, we can know the deficiencies of existing code models, thus motivating future research. To answer the aforementioned question, we undertake a systematic and rigorous evaluation on the efficacy of deep neural networks in foundational program analysis tasks. We use the word foundational here to represent static analysis that serves the foundation for various client analyses. And we face two primary challenges. Firstly, how to define prediction tasks that correspond to the foundational tasks in program analysis. Secondly, how to curate a dataset at scale that serves the tasks being defined. For the first challenge, we draw on two foundational problems in PL research, alias analysis and equivalence checking, to derive alias prediction and equivalence prediction. The reasons we choose the two analysis tasks are that they are among the well-established, important static analysis with lots of literature and applications. For the second challenge, we leverage the results of corresponding program analysis methods so that models can be trained on potentially unlimited amount of labeled data without any human effort in data labeling. There are some existing benchmarks for code models. For example, CodeXGLUE involves 10 tasks, including clone detection and code translation. CodeSearchNet is used for semantic code search tasks. Regarding research approach, we first define the two prediction tasks. Alias prediction is derived from alias analysis. It checks whether two pointer variables refer to the same memory location at a particular program point, and will return three possible results: must alias, may alias, and must not alias. We adjust the definition of may alias here. Two variables is may alias at a program point n if for some but not all executions to n, they refer to the same location. We define this way to exclude must alias from may alias. Equivalence prediction is derived from equivalence checking. It checks whether two programs are semantically equivalent. We follow Church et al.'s work to define semantic equivalence. Next, I'll talk about the training approach we design. First is generalized pre-training. It corresponds to the pre-training phase in the widely used two-stage learning approach. In this stage, the training goal is to learn general foundational properties of source code that is independent of downstream prediction tasks. We adopt the tasks that each model is trained with in their original pre-training stage. Specialized pre-training is the transition phase we designed between generalized pre-training and fine-tuning. Different from fine-tuning stage, which needs clean ground truth data, specialized pre-training aims at learning a coarse decision boundary for the specific prediction task with data that contains an acceptable amount of noise. The advantage of this is it allows models to exploit potentially unlimited amount of labeled data produced by corresponding program analysis methods. And in turn, it can help to more effectively adapt the models to downstream tasks during fine-tuning stage. For alias prediction, we propose a task called noisy alias prediction. In this stage, models first learn a precise decision boundary between must and must not alias, and subsequently learn a rough boundary between must and may, must not and may. For equivalence prediction, we design noisy functional equivalence prediction. Models predict whether two given programs have the same input-output pair and learn the coarse separation of programs with respect to functional equivalence. After the generalized pre-training and specialized pre-training, models undergo fine-tuning stage. The tasks are alias prediction and equivalence prediction. Only ground truth data is used in this stage, and the aforementioned coarse boundaries are refined. Now I'm going to introduce one of the contributions of the work, dataset CodeSem. We build our dataset on C, C++, and select 14 open source projects as shown in Table 1 to extract data from. I'll introduce the dataset for each training stage. First, for generalized pre-training, we extract all files that can be parsed by clone and randomly pick functions to generate for all generalized pre-training tasks. Then when generate specialized pre-training and fine-tuning dataset for alias prediction, we adopt sound-made alias analysis and sound-masked alias analysis. Since sound-made alias analysis over-approximates alias relations to ensure that all potential alias pairs are found out, it returns ground truth mask-not alias and noisy made alias, and the latter are almost certain to contain mask-not alias. In contrast, sound-masked alias analysis under-approximates alias relations, making it return a subset of ground truth masked alias pairs. Therefore, after we combine the two analysis results, we get ground truth masked alias pairs, ground truth mask-not alias pairs, and noisy made alias pairs. So far, we get the data for noisy alias prediction, and we only need to involve manual validation to verify the labels of noisy made alias pairs to get clean ground truth data for the fine-tuning stage. For equivalence prediction, we build an automated data pipeline to create the dataset. The pipeline consists of two steps. First, extract code fragments from the program of selected software. Second, test their functional equivalence dynamically. Since functional inequivalent code is knowing semantically inequivalent, we only need to manually confirm noisy functional equivalent code to get the fine-tuning dataset. It is worth mentioning that the data for each training stage is not duplicated with that in others. Table 2 shows the statistics of dataset CodeSem. Regarding evaluation, for the choice of code models, we select 4 deep learning models, which are CuBERT, CodeBERT, GGNN, and graph sandwiches. CuBERT and CodeBERT are sequence models. GGNN and graph sandwiches are graph models. As for program representation, for sequence models, we only adopt one representation, that is token sequence. For graph models, since there is no unified standardized representation, we consider 4. Specifically, AST with additional edges and leaves-only graph are the representation adopted in GGN and graph sandwiches respectively. We additionally introduce control flow graph and program dependency graph to explore whether there is a general graph representation so that graph models can achieve their best results. For statement representation, we adopt token sequence and AST. Table 3 shows the results of alias prediction. We can see that sequence model perform better than graph models, with CuBERT and CodeBERT achieving the accuracy of 89% and 84% respectively, while GGN and graph sandwiches achieve the highest of 78% and 81%. In addition, the accuracy of the same graph model can vary drastically with different program representation. For example, when GGNN switches from PDG plus token sequence to CFG plus AST, the accuracy drops 29%. We also want to explore whether the use information of alias would have an impact on model's performance, and we find that in most cases, embedding variables with use leads to a higher overall model accuracy than without. Occasionally, incorporating use can also hurt model accuracy. This may be caused by complicated usage patterns of variables that negatively affect the precision of their embeddings. We also find that models trained with our approach are almost always more accurate than those undergoing traditional pre-trained fine-tuning approach. And sequence models exhibit more balanced accuracy across all three labels, while graph models behave differently on different representations. On one hand, they achieve rather balanced accuracies while achieving the highest accuracy. On the other hand, their accuracies vary greatly depending on the alias type. Table 4 shows the results of equivalence prediction. All models achieve a comparable high accuracy, and CuBERT remains the best. Compared to alias prediction, the role of program representation is less significant in this task. Nevertheless, both GGNN and graph sandwiches show a swing in accuracy of 5% to 10% depending on the program representation used, and they both achieve the highest accuracy with PDG plus AST. Together with the results of alias prediction, we think this demonstrates the power of PDG as a principled representation for learning code models for foundational program analysis tasks. Regarding training approach, in almost all cases, models undergoing our training workflow are more accurate than those trained with pre-training and fine-tuning. Together with the results of alias prediction, we think this confirms the role of specialized pre-training stage in training models towards solving foundational program analysis tasks. At last, all models achieve balanced accuracy. We also conduct an in-depth analysis to gain an insight into models' ability to solve alias and equivalence prediction. For alias prediction, we find that the NL level information has a minimal impact on model performance. And although in most cases, all models become less accurate as the distance of alias pairs increase, they still achieve acceptable accuracy. For equivalence prediction, we first select a classic clone detector to confirm the validity of CodeSem for equivalence prediction task. And we find that the simple template matching approach is insufficient for recognizing equivalent programs in CodeSem. In the end, we select 3 state-of-the-art equivalence checkers and expose the challenges posed by CodeSem that are beyond them. Meanwhile, we find some weakness of models which should be taken seriously. For example, in alias prediction, more fine-grained embedding methods could be explored. And in equivalence prediction, train models to formally reason about program behavior can be a pathway forward. In this work, our primary goal is to evaluate different neural architectures. Therefore, we did not involve large language models. But we do think that the performance of large language models on foundational program analysis tasks is worth exploring. To conclude, we present a dataset, CodeSem, and design 2 new prediction tasks to evaluate deep learning models. We also propose a new training approach to make models leverage results of static analysis methods for training. And the results show that in general, all models displayed a satisfactory performance in both tasks. And that's all. Thank you for coming to my talk.
So, yeah, are there any questions of the audience? Otherwise, I have several questions. So, one thing that I was surprised is that like one of the nice things of static analysis is that typically you have this promise that most of what you get, you don't have false negatives, you only have false positives. That's usually what you, it's a one-way analysis. It's either sound or complete, typically when we do program analysis. So it's like people only have to worry about whether something, if it says equivalent, it's equivalent. If it says or the other way around. Usually if it says inequivalent, here is a proof. If it says equivalent, maybe it's equivalent. Or if it says these things may, if these things for sure alias, then they were for sure alias. And if it says they may alias, it means I don't know. So basically there is usually only false positives you have to care about, or only false negative, but not both. And in this vision, it looks like you have high accuracy, but essentially now I have to worry about the sum of the errors. It's like something can be wrong with 20% in probability in each direction. It can be either a false positive or a false negative. So do you have a sense of whether, like I would expect that you produce not just a yes, no answer, but some kind of a proof. For inequivalence, for example, here is a counterexample, and then I can convince you that it's inequivalent. It's not quite a question, but it's more like what is the goal of having a predictor of a yes/no answer when then we have kind of no sense of whether the answer can be trusted? That's at the high level. I know it's not quite a question. I don't know how to formulate it, but it's like usually what we like about program analysis is that it gives one-way answers. It's like if it says, yes, this thing works, it means it works. And sometimes it says, I don't know. But it looks like now with this approach, we have I don't know either way. Like we never get a for sure answer. Okay, maybe I'll move to my second question, which is maybe more of a question, which is like, have you thought about predicting not just the yes/no answer of? Oh, actually, Arjun has a question. No,
you can finish your.
No, I think I finished my first non-question, so you can.
Sure. Thank you for the talk. So I was curious about the examples where it goes wrong, right? So one of the things that you said is that natural language in the benchmarks don't seem to have an impact, which is a little surprising to me. I'm curious. Have you found that so? These models are sensitive to natural language. Even if you don't have comments, they're sensitive to things like variable names. So anything about that? Like, would you say like variable names seem to matter? Like if there's some sort of distracting variable name or like bad class name?
Yeah. We have conducted the related experiment, and we mask the variable name, function name, and comment, and to compare the performance of models, and the results tell us that mask the information. The human can understand it like information, and did not hurt the accuracy, and we believe that for these deep learning models. And we believe that these deep learning models can have an understanding of the semantic of the code, but but not with no regard to the under level information.
You can start coming. So I have another question. You can start disassembling there. But I was curious about, you said you have a new data set that you have open sourced, I assume, that people can build upon. So I was just curious, since this data set was released, have other people that you know tried to do similar predictions with different models? Have other groups used the data set and had different results?
As far as I know, still there is no one that use the dataset, but we keep it public, and everyone can have access to it.
Thank you so much. Let's thank the speaker again.